All right, we're moving into the last part of this course, last third of it, and that's torsion. So we started with axial stresses and strains. We were pulling on things, maybe pushing on them. In either way, we were applying forces along the axis, the longitudinal axis of the part. Then we moved into flexure. So we were bending beams, frames with beams in them. We were bending these things, flexing them. And now we're going into torsion. So we're twisting things. Now this particular course doesn't ever combine all of those, bend something, stretch it, and flex it, or bend and flex, flex, twist, and stretch all at the same time. There are methods to do that. That would be another course after this one. So we're going to keep them all separate for this. And so we're going to look at torsion today, or begin looking at torsion. We're not going to finish it. We're going to do probably three different sets of content on torsion. So we're just going to look at the beginning of it today, though. So torsion, we mean we're twisting something. So we are going to limit our torsion calculations to a particular type. And the type I'm talking about has to do with what we're torquing. And that is that we are going to limit ourselves to circular cross sections. So tubes and pipes and rods and things like that that are circular. So this thing, it's circular. Obviously, you can apply torque and torsion to non-circular, like this hex-shaped bar, well, pin. You could do that, but one of the things we're going to do for our calculations in our development of torsion is going to make that not work for this particular calculation. And we'll get to that later on. But first, let's go in and let's define a couple of variables and see where we can get from there. So let's start with a solid rod of some kind of metal material. It doesn't have to be metal, but most of the time what we're in the context of this course doing is these are transmitting some kind of torque. So there's some kind of power transmission from one location to another. Maybe this is the shaft between a motor and a wheel or a pulley or a gear or something like that. And so they're usually made of metal. So we're going to draw this one kind of in 3D, the best I can anyway, in 3D. So something like this will be our shaft. Now the end on the left, we're going to say that this end is rigidly mounted to something. So maybe it's the motor, maybe it's welded to a wall. I'm just going to draw that with a, just kind of little blob over here that's going to show it connected to the wall. Basically so that we can envision this thing actually twisting when we go to apply a torque to it. All right. But before we apply a torque to it, so here's our little rod or whatever it is. A lot of times these are going to be rods and shafts, pipes and tubes, things like that will be the application. So before we torque it or twist it, let's draw a line. Maybe we're not really drawing a line, but we're going to, on our paper, we're going to draw a real line down the center of it. So this is on the outside, we've drawn this line. Let's give this line a length. Get that out of the way. Let's just put the length down here so it's kind of out of the way. And this length will just be L, capital L. All right, so that'll be one variable that we have to deal with, is just the length of the line. Other things that we would need, let's find the center. Let's just say the center is right here. We're going to define one variable that is going to be the radial distance from this center. So let's just draw it over here somewhere. So some distance, and we're going to call that rho, and that's going to be the radial distance from the center. And we're using rho instead of something like R because later on we're going to come in and do a polar coordinate setup, and so rho makes more sense with that instead of just r. But it doesn't really make any difference, but typically you have a rho as the radial distance from center. Now, most of the interesting stuff that we're going to be dealing with in torsion happens on the surface of this shaft or tube or whatever it is. And so we use a special variable when rho is out here at the very end, and we call that C. So C is rho, but at the surface. So it's the outer radius of the shaft or whatever it is. And it is a radius, it's not a diameter, so we do have to make sure that we keep that straight, because a lot of times these shafts and tubes are specified by diameters and not by a radius. All right, so now we've got a shaft. It's got a green line drawn on it. We know a couple of variables here and one variable for the length of the shaft. Now let's apply our torque. So let's take and put a torque on this thing. And T is just going to be the torque. And it's, you know, for now we're going to assume this is a flexible type material and we can really twist it. And if we do, then this line will go from here and, well, let's look first at this point. Let's draw it with, trying to figure out what color will make the most sense. There's a point on the end of this line. If I twist hard enough, that point will move, maybe to here. So from one location to another location. And the line, the green line, would go from here and it's going to twist around and look something like this. So it's in a new position now. So this is position 1, that'll be position 2. Now, this, if we were to connect these same dots to the center, if I kind of already got one labeled C, they'd still be distance C, right? But it would be at a new position there. So that's also C. What's interesting here is the angle right here. So that this radial line, we're not spinning the shaft, we're just twisting it. And we twisted it to where this point moved from here up to here, and we twisted it through, and this is going to be small, but theta. So theta is called the angle of twist. How many degrees, now it's radians, how many radians did you twist this shaft? And when you calculate it, we're not going to calculate this one today, but when you do calculate it, it comes out in radians. Obviously, you can convert it to degrees later on if you want to, but when you calculate it, it comes out to radians. All right. So now let's get into figuring out how does any of this relate to shear stress, torsional shear stress. That's what we're trying to get to. And right now I have something, if you imagine like this is a spring, or maybe you are here and suddenly you're holding on and you've been twisted around, pulled and stretched. There's a strain that happens here from one point to another. That point didn't just move, but it had to strain to get there, because we didn't just spin the shaft. We're not doing this. We're doing this, where we're twisting part of it, and obviously it's not two parts, but the whole thing, we're twisting this point from here around, and so all that material in there had to strain. So there is a strain, a shear strain, and we used gamma. This was weeks ago when we did a shear strain. Now when we did shear strain, we did this little picture. We said we had a box, we put a force on it, and it strained. You know, it didn't, the bottom didn't move, but the top did, and so there was a strain there. And we said that that gamma was the shear strain. we have the same type of thing here. It's just on a circle, or it's on the surface here. So we have an original point, and it moved over here. It looks like we had an original point that moved to here and created the angle that was created by that movement over this part side that didn't move. That was the shear strain. So we have that same deal here. Let's call this H. Let's call it H sub C, since it's out at the surface. C is the variable we're using for when rho is at the surface. Maybe we should use S, but we use C. And so here is the same gamma, this angle. Now, technically, this is an arc length. It's not a straight little line like we had here, but also this probably created a little bit of arc also. And typically, these are not twisting a lot. Like if you have an actual machine with a shaft that's delivering power from one place to another, it's probably not twisting that much. So this is I've exaggerated it a lot to be able to show you things. So gamma is equal to this length. Now technically it's in the inverse tangent. So let's write it out. Gamma C. So this is at the surface again, because we could have a different one at the center point here. That point, no matter how much we twist, that point never moves. So there's actually no shear strain at the very center. And there's a bunch of shear strain at the surface, and there's, smaller and smaller amounts the closer you get to the center. So there's a variable shear strain in the inside of the part here. But we're looking at the outside, C. So it equals the inverse tangent of this side. Now we're treating this as basically a right triangle. So here's one base, here's a side, and here's the hypotenuse. So this angle would be inverse tangent of HC over L. And we said that typically these are not twisting a lot. It's a very small amount of twist. This point doesn't really wrap around a lot of times unless the thing is really, really long. And so when we have really small angles here, we can say that pretty much this shear strain is equal to HC over L. You don't have to do the inverse tangent when you're dealing with these really small angles in radians. Okay, HC is this distance that the point moved from here to here. Now on this one, this would be the same idea. I think we called it delta maybe on this particular setup. So that distance is this arc length. And we can calculate that arc length with this radius times the angle that the point moved through. So I'm going to replace HC with the distance HC, which is theta times C, and then over L. And now we have an equation that will give us a ratio here. Now I'm going to rewrite this equation just to make the ratio clearer. So this equation could also be theta over L equals gamma C over C. So that's useful to us. It doesn't get too close yet. Like we don't have a shear strain, or we don't have a shear stress. We do have a shear strain actually. We have a shear strain right here, but we don't have shear stress yet. Now, this is the largest shear strain, the C, so it's at the surface. But we could take any point on here. I'm not going to draw too much of this one because it gets really crowded. But let's imagine, well, we have this arc right here. So let's imagine this point moves from here up to here. We would get a very similar relationship, except now this would not be the angle that would be gamma C here would not be gamma C. It would be a little bit smaller. It'd be gamma 1 or whatever, gamma rho we could call it, whatever we want to call it as far as the shear strain inside the shaft. So we could call it whatever we want to. Maybe we'll call it just gamma rho. That probably works. So we could have gamma rho is equal to the inverse tangent of now not HC, not this distance, but this distance. Now the interesting thing here is that this little distance right here is rho. So I know we're getting really tiny there, but that's rho. And it could be anywhere. You know, rho can vary from 0 to C and anywhere in between. So that's rho. And L is still L. Theta is still theta. So what we would end up with is a very similar, if we wrote it all out, we'd end up with a very similar equation that would say, well, theta over L is equal to gamma rho over rho. So this is telling us that we have two things equal to theta over this ratio of theta over L. So both of these terms equal the same ratio, so they equal each other. So that's kind of useful. So let's go ahead and write that down. Let's go to a new page. We'll have to come back to this page, but let's go to a new page and just write down the fact that these two both equal theta over L, so they must equal each other. All right, so that would be something along the lines of gamma at C, so the shear strain on the surface divided by the outer radius is equal to the shear strain inside somewhere divided by that radius of where that shear strain exists. So that ratio, those ratios are the same. Now, these are not shear stresses. These are shear strains. But we also early on talked about the relationship between axial stress and axial strain, and we drew something like this. Something like that. And we had stress on the y-axis, and we had strain on the x-axis, and it was sigma and epsilon, axial stuff. There's a similar plot for tau and gamma. So tau is shear stress. Let's shear stress. And gamma is what we've been talking about this whole time, shear strain. And the scale of this graph would be different, but the general idea is the same. You would do a different test. You wouldn't do a tensile test. You'd have to do a shearing test to generate a plot like this. But you would get something similar where there's a linear elastic part and then there's a plastic nonlinear part. Generally, you want your machines and your structures and whatever you're designing to operate in this elastic region. And remember from the stress strain plot, we called the slope of this line E, the modulus of elasticity. Well, you have a similar thing, except we're going to call it G, the modulus of rigidity. So G is the same kind of thing that E is, where E was the a modulus of elasticity. So a material that had a high modulus of elasticity meant that this slope was very steep, and it didn't stretch a lot for the amount of stress that was on it. So same thing here, except it doesn't twist a lot for the amount of stress that's on it. If the modulus of rigidity is really steep. If it's really shallow, more like what I've drawn, then it does stretch a lot for the amount of strain that's in the object. And there's also, as long as I want to stay in this elastic region, I have a similar thing to Hooke's law for axial stress to this, where I can say that tau is equal to G, modulus of rigidity, times gamma shear strain. So that's just the slope. That's the equation of this straight part of the graph. This is the equation of this line right here. And it's very similar to sigma equals E times epsilon, right? Hooke's law for axial stress. All of that to say that I've got shear strain in here. And I know how to get from shear strain to shear stress with this equation. So let's take and multiply both sides of this equation times G. So multiply both sides times G, and then I will have, this is maximum shear strain times G would be maximum shear stress. So G times gamma. So I'm going to do tau max over C still equals, this is a function more or less. It's basically the shear strain at any point R, rho, multiply that times G, and I have tau at any point rho, so the shear stress at any point rho, divided by rho. So now I at least have shear stress, but it doesn't actually help me that much because it basically says that, hey, if I know one of these, I can calculate the other one. And I do know the shear strain and the shear stress at the center here is 0, but that doesn't really help me do anything. It basically says that it would equal 0 at the center, and it doesn't give me any actual equation I can use. So I need to dig a little deeper to figure out how to get a useful equation from this. So let's take this in view here and look at it head on. So it's a circle. We'll look at let's look at this size circle. All right, so there's the in view of this guy. So it has a center point, and we do know a couple of things. We know that at the surface is where I have maximum stress. Looks like we're kind of getting towards the bottom of the screen. There we go. That's at the surface. I'm going to draw one point on here with the surface. Maximum stress is out there. I also know that there's 0 stress at the center, because there was 0 strain. So if there's 0 strain, then there's 0 stress. And I also know, sort of from here, I guess you could figure it out from here, that it is linear. The shear strain is linear from the center out to the maximum at the surface. So basically I could draw a straight line connecting this point. And I'll just finish this off with, I could have a profile for the stress, something like this. So the shear stress at any point in this cross section is going to be maximum at the surface and 0 at the center, and it's going to vary linearly all through there. So there's kind of the stress profile. Now, if it varies, it's a variable, then the only way I know to deal with that is I'm going to have to integrate across this entire surface. And since it's a circle, the best way to integrate this is in polar coordinates, where we integrate rings like this. So put a ring there, and let's draw the center part of this, something like, I don't know, that. So this ring here, do I have a nice green color I can shade that in with? I thought I had one, but I seem to have lost it. Oh, here we go. All right, so this little area, I would start with a really tiny one in the center, basically a dot, and then make that ring grow and grow and grow across the entire surface of this circle to integrate across it. So this ring would be my differential area. This would be dA, and it would have a thickness, let's put it over here, d rho. This would be infinitesimally thin, right? So it'd be really just lines, all concentric lines that I would add all of them together, basically, to integrate across here. All right, so that at least helps me know how I'm going to integrate this. But, what do I actually integrate? So we have to remember a couple of things. We have to remember that in general, stress equals a force over the area that that force is applied to. So if that's true, I could rearrange this and say, well, stress times area must equal force. And I have stress right here, and I have an area that I'm integrating from the center outwards. So if I multiply tau max times dA, that will give me force. This force is useful because the thing that's creating this stress to begin with is a torque. I didn't draw on here. We drew it. Where'd we draw our other picture at? Under here. I don't know where I moved it to. Well, anyway, there was a torque on the outside. I seem to have lost it now. Here it is. No, that's not it. Here it is. There it is, that torque that was causing all this stuff to begin with. So there's a torque outside here. Now in engineering, we use torque and moment. They're really the same thing as far as the way you would calculate them, but we use a specific word in a specific scenario. So when we were doing beams and trusses and frames and all that, we were using the word moment to talk about how a force was applied at some distance and it created some kind of bending or flexing or even a rotation. Torque, we're going to specify that a torque is the same idea. There is a force at a distance, but we are specifying that it is creating rotation or twisting about the longitudinal axis of a shaft. So they're really the same thing, but we use different words. Torque to mean when we're delivering some kind of rotation along the length of a shaft versus a moment being a flexure or a bending or something like that. But they're the same thing. All that to say that this torque was created by a force that was applied at some distance. And that force is right here, or it can be right here. Stress times area. Stress times area will give me that force. So let's take this equation and let us rearrange it a little bit so that we actually have the tau rho, tau is a function of rho, by itself. So basically just multiply times rho equals tau max. This is not a function, it is just the maximum shear stress, which is on the surface of the shaft, times rho over c, right? So move the rho over there, basically. Now, I have stresses in both of these. I want to turn this stress, the one that's a function of rho, so rho goes from the center out to the surface, I want to change that one into this force that goes from the center out to the surface. So this force actually would also look like this. And it would get larger towards the surface. Usually the force is applied at the surface. Obviously you can't normally apply force inside or something like that. Sometimes it is applied to the inner surface though. Maybe if this is a sleeve that slides, well, like this. You know, if the sleeve slides over a pin and you're twisting this, then the force on this guy is actually applied on the inside. So you can apply them on the inner surfaces, but normally you can't apply them inside the geometry itself. All right. Anyway, let's multiply this whole thing times dA. Like that. So what that does for me is now I have tau as a function of rho times dA equals all of this stuff, tau max times rho over c dA. So I have all of that. All right. So now I've got tau stress times dA. Stress times area is force, so this is a force. But it's the force, since tau was a function of rho, this force is also a function of rho. This side I'm going to leave the way it is. Tau max times rho over c dA. Okay, that's interesting. But I really want to relate my stress. I've got tau max in there, so that's what I'm mostly interested in, is I want to know what tau max is. I've got it in there, but I want to relate it to the torque that's causing all of the strain and stress. So force times a distance, in this case rho, is this outer torque. So let's start with this. In fact, I'll just copy it down again. F as a function of rho equals tau max times rho over c dA. Let's multiply this whole thing times rho. All right, now I have rho times a force. Now it's a function. It would have probably... Oh, did I never write? I never wrote this down, did I? I never actually... Oh yeah, I did write this. It would have probably been better, instead of writing f as a function of rho, since I had the dA in here, I should have probably written this. Sorry about that. Should have written it as dF. So it's still a function, but now it's a differential force, because remember the force changes from the inside to the outside. So I should have written that as dF. So let's fix that. dF. All right, sorry about that. Now I've got rho dF equals, here I've got to multiply rho times all of this stuff. Now I'm going to put rho, I already have one rho in here, so I'm just going to do rho squared. And all of this thing is dA. Now if I were to, I have dF over here, dA, if I were to integrate both sides, basically from the center outwards. Now we don't always have solid shafts. You could have a hollow shaft, and there's another variable that I haven't mentioned yet. Let's go ahead and mention it. So let's just pick this one. This is kind of an aside. All right, so this is a pipe or a tube. It's hollow either way. And we've already established one of our variables is C. So C is the outer radius. You have to be careful with this, because a lot of times when you're given a problem to solve, you're told shaft information in the terms of diameters, because you don't normally buy a shaft based on its radius, but based on its diameter. So, but the equation is looking for radius. But if it's hollow, we have another variable that tells us about the inside. How far is the inside? So B. B is inner radius. So I'm actually going to integrate from B to C. So from B to C here, maybe I'll just say that it's over the area, whatever the area is, but we're going to go from the inner wall, which could be 0. B could equal 0, right? So you could go from all the way to the center, if it's a solid shaft, out to the surface. We'll just put an area, realizing that it might be hollow. So this guy, if we go back to our picture here, I'm integrating this force from wherever the center is to the surface and multiplying it times each one of those little r's. I'm doing integrating it over that surface. So this whole term becomes the applied torque. So this side just becomes torque. And this guy becomes, it's an integral. Now tau max is the one value for the maximum shear stress. So it's a constant, it's not a variable. C is the one value for the outer radius. It's a constant, not a variable. So both of those can come out of the integral. And then rho obviously is a integral variable because it's the distance from the center outwards. End with this equation. This term is going to be different for every cross section, right? Because everyone has different size diameters, internal radius and external radius. This thing is called the polar, and there's a couple of different things you can say. Polar, what I will mostly say is moment of inertia. So similar to the way the I moment of inertia that we had for beams, a larger moment of inertia meant that the beam was less likely to bend. A large polar moment of inertia means that the shaft is less likely to twist. You might also call it the polar 2 here, so second moment of area. So I was also just called the second moment of area. The first moment of area was these part of the numerator for the centroid. Remember, it was just y dA. This is rho squared dA. As long as this relates back to a circular shaft, whether it's hollow or solid, then this term will equal pi over 2 times c to the fourth minus b to the fourth. And instead of writing this most of the time, we give it the variable j. So j is the polar moment of inertia, or the polar second moment of area. So we would have this equation typically as written t tau max over c times j, except normally you're not solving for t. You normally know t, it's the external torque that's applied to the shaft. Normally you're solving for the maximum shear stress. So normally how you see this is tau max equals t times c over j. That's the normal torsional shear stress equation that you're going to use. Now there is a slight variation if we go all the way back to here, where there was this idea that the shear strain was proportional to the shear strain inside. So this is the maximum shear strain. This is the shear strain anywhere inside the shaft. They were proportional to the ratio of C over rho. And so you could potentially see this equation written as just tau as a function of rho. So anywhere in the shaft is equal to T times rho over J. You normally don't calculate this one because normally you're interested in the maximum shear stress, but sometimes when you have something like this where there's an outer and an inner thing that interface with one another, sometimes you do want to know the shear stress on that interface between the two. So that would not be the maximum on the outer surface of like the yellow cap here, but it should be the shear stress on the inside of the cap. And so in that case, you'd use this one where rho is B, the inner radius of the cap. Because maybe you've glued these things together and you're twisting and you want to make sure that there's not so much shear stress on that glue that it breaks the glue. That might be a reason to use this equation. Most of the time you're going to use this equation. All right, let us actually do an example with this and we'll be done for today. And Wednesday we'll come back and do some more. We didn't talk about angle of twist yet. We still have the idea that what if you have a whole bunch of torques on here? Yeah, how do you deal with that? So there's still more stuff to deal with, but let's do a simple one today just to show how it works. So let's basically start with the same setup we had when we derived all this, but with numbers. There's our shaft. Let's put a torque on it. 50 Newton meters. We could give it a length, but notice the length doesn't affect the shear stress. Only the torque, the radius, the outer radius, or the inner radius, you know, if you're doing the row version, and the shape of the cross section. In this case, basically the size of the cross section. How big is the circle? Let's do a hollow one so that we do have practice with a hollow one. So this one's hollow in here. And let's make this side attached to the wall. Okay, and we need to know the dimensions of this shaft. So let's say that the OD, so OD is outer diameter, that's an O, not another D. OD is 75 millimeters. ID, inner diameter, 50 millimeters. Okay. We want to find, so we're given this, and we want to find tau max. That's all we want to know. So tau max equals T, which we have here, 50 Newton meters, times C over J. So we have 50 Newton meters times C is the outer radius. We have the outer diameter. We have it in 75 is the diameter, so divide by 2 for the radius. That is millimeters though, and we want it in meters, so let's divide by 1,000. 0.0375 meters. Divide by J, the polar moment of inertia, which it is a circle, it's a hollow tube, so pi over 2 times C to the 4th, this is C, minus B to the 4th. B is the inner radius. We have the inner diameter at 50. Divide that by 2 and divide by 1,000. So 0.025 meters. And if we solve this, we should have the stress in the shear stress, maximum shear stress on the surface of this shaft. So let's see, 0.0375 to the 4th minus 0.025 to the 4th times pi over 2. All right, that's our denominator. 50 times 0.0375 divided by that denominator is 752,190.7. Units, newtons, we have Newton meter squared in the numerator, meters to the 4th in the denominator. So this is newtons per meter squared. Newton per meter squared is a Pascal. So we have 752,000 pascals, so kilopascals. That seems like a big number, but it's actually a really small number when it comes to metric units. Pascals, your materials are in the 200 million Pascal for yield strength. Now this is a tau. This is a shear strength or shear stress. So you do have to compare it to a shear strength. So the shear strength for some generic steel is, I don't know, 200 gigapascals in tension. Remember that you have to have a model, whatever kind of model you're using, to figure out the shear strength from the tensile strength if it's not given. The one that we're using is the super simple maximum shear stress model, where we just divide by 2. So if we had a tensile strength of 200 gigapascals, we would have a shear strength of 100 gigapascal, not giga, megapascals, 10 to the 6th. So 10 to the 6 pascals. We're way under that. We're at 752 times 10 to the 3rd pascals. So we're not even close to yielding any of this material with the 50 Newton meters. And for size, if I had to drew this thing to scale, it would only be, I might even have a circle that big. I didn't measure. Yeah, this circle is basically 75 millimeters. And then where's a 50 millimeter one? This one is 50 millimeters. So to scale, 1-to-1 scale, that's the pipe size that this thing would actually be. So it's pretty thick. You know, this is 12.5 millimeter. Oh, I didn't talk about that. This dimension here, sometimes instead of being given the outer diameter and the inner diameter, sometimes you're given one of those and T, where T is the wall thickness. So if you know the inner and the wall thickness, then you can figure out the outer. If you know the outer and the wall thickness, you can figure out the inner. So a lot of times you might have pipe, if you're specifying pipe, you'll have the outer diameter and the wall thickness. And you won't be given the inner diameter necessarily. One thing to be careful with is, in our case, a lot of people accidentally, like they're just getting a hurry or whatever, and they do, oh, the outer diameter is 75, inner diameter is 50, and so my wall thickness is 25. But if you do that math, outer minus inner, that's actually 2 wall thicknesses. So be sure you divide that by 2 so that you get a wall thickness of, in this case, 12.5 millimeters. Okay, I think that gets us enough into torsion. We were really just trying to get right here. Where does this equation come from? It's better to at least have some idea of where it comes from, even though we did make the one little mistake there. Have some idea of where it comes from other than just, hey, here's the equation, TC over J. But this is what we're trying to get to. All right, on Wednesday, we'll do some more of this. We'll talk about this angle of twist and what does it do and how do you calculate that. And we'll probably, I don't know if we'll Wednesday or Thursday, but between the two of those, we will also talk about power transmission, because normally this shaft is twisting because you are transmitting power from one place to another. So I'll see you on Wednesday. Send me questions if you have them, and I'll try to answer them. And see you Wednesday.